Okay, so what is fatigue? Do you remember from the previous lecture? Fatigue, Umar, Hamza?
Something like it gives force and break or something like that.
And Hamza, do you remember something?
The force to break something.
Okay, okay. Now focus on this shaft, right? This is a shaft. Okay, so this is a motor, and this shaft is rotating like this. Okay. So this is okay. Forget about this. This is a beam, right? And I stretch it in this direction, right? So it will become like this. Okay. Okay.
Okay.
And again, if I deform like this, then it will become like this. This is the stage 3, right? And again, if I deform in the previous manner, then it will become like this. Again, like stage 2. Okay. So this is what we called fatigue loading, right? Are you listening to me or not? Hello? Hello? Are you here? Hello?
Yes, clear, doctor.
And what about Umar? Umar? Hamza? Is Umar here?
Amar, hello. Maybe the internet is bad.
But my internet is good now. I have updated my router and all the cables and all the things.
Maybe his internet.
Okay, so can you message him on the WhatsApp that please connect?
Okay.
Hello, Umar is coming or not? Hamza?
I am waiting him in WhatsApp.
Okay. So tell Umar that please connect with the class because it is very important lecture.
Yes. Continue, Doctor. He will see the recording.
Okay. Okay, so you understand the fatigue.
Yeah.
Okay, so the fatigue is basically the stress which varies with time, right?
Yes.
So I can represent it with the help of a sine wave, right? So in the start, the fatigue is very high, but it becomes low, and it becomes minimum here, and again it starts to become increasing, right? So
Yes.
this is the maximum value, this is the minimum value of the stress, and this is the minimum value. This is the average value, right?
Right.
Okay, so the key parameters are the S, right? S is what we call the amplitude, right? Sigma M is called the average, and the cyclic frequency is the frequency from this up to this. This is frequency. Okay.
Okay.
Okay. So fatigue is the main responsible for the failure, right? So fatigue can occur even if the maximum stress is less than the yield stress. So it is responsible for 90% of the mechanical engineer failures. Okay, so fatigue limit. Okay, so fatigue limit, we define this quantity fatigue limit. It is, do you have the notes which I sent to you?
Yes. Didn't we say it?
Yeah, it is what is the definition of fatigue limit there?
I don't remember very well.
Can
I
you?
only see it. Today I will study it very well.
Okay. Okay, so it is the minimum amount of stress below which failure will not occur. Okay, so what is mean by failure?
Failure?
Yes, failure. Failure mean the material break, right? The material break.
Yes.
Okay, so this is failure, right? So fatigue limit is the minimum amount of this cyclic stress below which the failure will not occur, right?
Right.
Even if you continue it for a very long time, then the failure will not occur. Okay, and there are some materials for which there is no fatigue limit, right? So like
Yes.
iron, steel grades, there is no fatigue limit.
Yeah.
Okay, so the crack growth, right? So what is A? A is the half length of the crack. And delta K is basically equal to sigma into square root of A, right? Sigma is the stress, A is the half length, and M is basically, it is a variable which can range from 1 to 6. It is a constant, right? And N is the number of cycles. For example, what is mean by cycles? Cycles means that, as I told you, this, I draw this figure. So I cycle, load it first, like, right? Then I unload it and it becomes a shape like this. And if I again load it like this, so it is the first cycle, this is the second cycle, and this is the third cycle, and we continue it, right? So basically we have the number of cycle on the x-axis and the stress on the y-axis, right?
Yeah.
So N basically represent the number of cycles, fatigue cycles. Okay. So failed rotating shaft crack grew even though K maximum is less than Ks. Okay. So the crack growth, right? This A will become larger. A will be larger. F, these conditions occur. 1, 2, and 3. Okay, so sigma increase, crack gets longer, and the loading frequency increases, right? So if you increase the stress, then the crack growth, the material will eventually fail immediately. And if the crack gets longer, right, so it will break suddenly. And if you increase the loading frequency, for example, you apply 10 kilonewton load after 2 seconds, and you increase it to 20 kilonewton after 2 seconds. So it means that you increase the loading frequency and it will increase the crack growth, right? And the material will fail quickly. Okay, so how can we improve the fatigue life, right? So these are basically the two methods, are the 2 points which you have to remember. Okay, so when we enforce the compressive surface stresses in the material, then the fatigue life can be improved, right? And in the second method, if we remove the stress concentration. Okay, what do you mean by stress concentration? Stress concentration means that, right? So let's say this is a liquid. Do you know liquid?
Yeah, liquid.
Okay, so this is a hard liquid of the melted iron, right? Melted iron. You understand what I'm saying, right?
Yeah.
Okay, so this is the melted iron, right? And I solidify it. It becomes solid like this, right?
Yeah.
So at some point, it will have the air bubble, right? Air bubble. Have you seen the air bubble in the ice?
Yeah, yes.
So at the same concept, air bubbles also formed when we solidify some metal, right?
Yeah.
Okay, so these bubbles are basically the stress concentration areas. So if we remove somehow these bubbles, then we can improve the fatigue life, right? And we can improve this by carburizing. Okay, so what is carburizing? Okay, this is my iron, right? And I diffuse. Have you studied the diffusion chapter? Diffusion, chapter 5.
Yeah, the diffusion.
Yeah. So have you studied this chapter?
Which number?
Chapter number 5, I think.
Yeah, study.
Okay. So by diffusion, this is what we call carburizing, right? We insert the carbon atoms here. So the surface become very hard, right?
Yeah.
So if the surface become very hard, then the fatigue life will be improved. And fatigue life means that it will resist longer loads for longer amount of time. Okay, so now this is an important phenomena, creep. Okay. Okay, so you are mechanical engineering, right?
Yeah.
Okay, so this is a shaft. This is a motor, right? This is an electric motor, and it has a shaft like this, right? Okay, so this is a shaft. And in the industry, let's say there are temperature, right? The temperature is 50 degrees centigrade, where it is operating, right? And there are loads on this shaft. So because of this load and also its weight mg and this temperature, the failure will occur, which we call creep, right? So the deformation which occurs at the constant stress, right? Versus time.
Yeah.
This is what we call the creep. Right? So creep is basically we represent in the form of strain. What is strain? Do you remember the Parmula strain? Delta L by L.
Yes.
Change in length by original length. Okay, so if this change in length by original length occurs at a constant space, right? So this is what we call creep. Okay, so if I plot this creep with respect to time, right? If I make a graph of this, so it will have three regions. One is primary, secondary, and tertiary, right? Okay, so first of all, from here, the material will start, right? So at the start, it will have instantaneous deformation, right? This deformation will occur very quick, right? Because if you
Yes.
if you reach here stress, the creep has some value E, right? It has some value. It is not zero here, right? The Y value, let's say this is Y axis and this is X axis. So the Y value is not zero here, right?
Yes.
Okay, so the instantaneous, it occurs in a very short amount of time. So we take the time equal to zero. Okay, so the red color is the primary region, right? So the primary region, it means that the creep is decreasing with the time. As the time is passing, as the time is increasing, the creep is decreasing, right?
Yes.
Okay, and the blue one is what we call the secondary creep. The secondary creep is basically a straight line. If you see, it is a straight line, right? You see it?
Yes.
The blue
It's
one
not
is,
slope.
yeah, it is a constant slope, right? Constant slope.
Yeah, constant.
And it has a negative slope, right? Okay. So the constant slope occur at the secondary, and at the tertiary slope, it increases with time, right? So it has a positive slope. So do you have notebook and ballpoint?
Again, Doctor?
Please write these so that you can remember. It can be asked in the exam that what are the region of the creep graph, and please
Yeah.
Okay, so please write it down. Okay, so creep versus temperature, right? What is Tm? Tm is the melting temperature, right? So the melting temperature,
Is it lagging or not?
what?
Okay. I thought it was lagging.
No. I was just
Yeah. No. Yeah, no problem.
I was managing the team. Okay, so the melting temperature is in Kelvin. Okay, so if the temperature is greater than 0.4 times Tm, for example, the melting temperature, the Tm for the steel is 350 degrees centigrade, right? Okay, so if I want to convert this temperature to the Kelvin, then what should I do? Do you remember?
Again?
If I go from degree centigrade to the Kelvin scale, Kelvin.
Plus 273.
Yeah, so 350 plus 273, right? So how much does it come out to be?
Wait, I get the calculator.
Okay.
135. 1623.
Okay, so it is 163 Kelvin, right? And
Yeah.
now if this temperature is greater than 0.4 times 1623, this is the temperature at which this material is operating, right? So for example, if I gave you the example of this material, right? So if the condition is such that the temperature is very high and it is 0.4 times its melting temperature, right? So if I multiply with 0.4, so it comes out to be 649.2 Kelvin. 649.2 Kelvin. And again, if I convert to degree centigrade, minus 273. So it comes out to be 376.2 degrees centigrade. Okay, so if the factory or the plant temperature is greater than the 376.2, right? So the creep will be dependent on the temperature, right?
Yeah.
Okay, so less than this temperature, there will be no effect on creep, right?
Yes.
Above the 0.4 times the melting temperature, if we increase the temperature, right?
All right.
So
Dr. Omar will join now.
Okay.
He told me what's up.
Okay, okay, tell him to join.
Okay. He said he cannot. The link is not correct.
He will link now. Okay, let's end it. Okay, let's end this meeting and start a new meeting, right?
Okay.